Hello again. Today I will talk about DETR object detection model authored by Facebook researchers for detection with transformers. And here's the brief overview of it. So I have a previous video about the actual algorithm and how everything works. This one will be more about training one yourself, re-implementing the benchmark, and reading the code. So here's the plan for today. So first, how to train your own model, how to get the initial data, how to set up the repository, run it, and get the same results as Facebook researchers reported on the Coco dataset. Second, I'll talk about my debugging setup, about Jupyter Notebook and Python debugger that helps me navigate source code for models like these, to run the code, to debug the code and step through it line by line and maybe print out intermediate variables, which helps to read the code and understand what's actually going on there. Then we'll talk about the data, so which data sets are used, data loaders, image transformations, and so on. I will read the actual source code for DETR for that. Then we'll talk about model architecture, again, looking at source code for DETR loss and the training loop. All right, first, how to do it yourself. The model itself can be broadly divided into two parts. So the first part is the so-called backbone, which just uses convolutions similar to previous models like ResNet 50 that was trained back in 2015. So this one is actually trained on a different data set called ImageNet. I also have a video about that. I have a video about this specific ResNet model and the ImageNet dataset and reading the source code for that. But basically, it's an older dataset. It's much bigger, so it has 150 gigabytes, thousands of classes, and 1.2 million images. So it is a bit challenging to download that and to train something on that. And the images themselves are high resolution, mostly canonical representations of objects. But we'll not do this today. So we just get the final weights for ResNet 50 from the Torch Hub. And then the rest parts, the transformer and the queries and so on, that we'll train from scratch. So they are trained using the Coco dataset. It is much smaller, only 20 gigabytes, 90 classes, about 100K images. It's curious because this sort of dataset turns out to be enough for object detection tasks, and it actually works better than ImageNet. And the main explanation for that is that it has non-canonical representations of the objects. So in ImageNet, if you want a picture of a dog, you would have it right in the middle of the image, facing towards you, and this is so-called canonical representation. So it's unobstructed, it's facing towards you, it's in the middle. Now in Coco dataset, you would have many objects. Objects might be obstructed, or only part of the object will be present in the picture. They might face away. You might only see like a really small part of the object. And this is how it is in real life. And turns out we don't need that much data to be able to detect objects, to learn to detect objects. And this sort of more challenging data works better for real-world applications. Right, so first let's go get the code. So it is located in this Facebook research DETR repository. So you can just go ahead and clone it somewhere. Second thing you will need is the actual dataset. Since we are training the proper model, I recommend to download it in full. So here you would need train images, validation images, and then the annotations. So it will be about 20 GB in total. Once again, this is just the Coco dataset download website. So you would need to download it, unpack it, and you would have the directory structure ready for training. So here I have it downloaded and unpacked. So it has 3 folders: annotations with the labels, train, and val with the actual images. And then I also have the repository, the DETR repository, that contains the code to run it. So repository is pretty much self-explanatory. They have a lot of instructions on how to set up for detection. They have some notebooks with some cool demonstrations, like this one, where they actually visualize tension masks and so on. And finally, to train the model using just the Coco dataset. So in here, they use the Torch distributed launch module to launch it. It is only needed if you want multiple GPUs. If not, you can just run the actual main.py script just with Python. Another thing you might need to do if you just get started with this is to install requirements. So this is how I do it. So just type Python pip install -r requirements.txt, and it should install all requirements. So the only thing worth noting here is that you need to pay close attention to what sort of version of Python you use, because you might have Jupyter Notebook, you might have Visual Studio Code, you might have PAP installed, and then the actual Python interpreter, and they might all refer to different versions of Python. So to help with that, I just always invoke the Python itself, and then ask it for the PIP module to install something. That makes sure that so the Python 3.9 is the one I usually use for training. So I'll always invoke this Python, the pip, and I will use the same in Visual Studio Code, in Jupyter Notebook. So it will work for a little bit, and that's it. So everything is now installed. I can run it. So this is the actual launch command. So I just run main.py. I need to provide the path to the dataset where we store the train validation and annotations. And I also provide device MPS. So I'm currently doing that on my Mac, just because I'm recording a video here. On Mac, it will be MPS. On everything else with GPU, it will be CUDA. So let's go ahead and run it and just wait until some iterations start to go. And it is started. So we can see that we started the first epoch. It says that it will take 21 days on a Mac to train just the first epoch, and I believe we need something like 300 of those. But with a proper GPU, it will take about maybe a week to train the whole thing, depending on like how many of them you have or how powerful it is, maybe even less. So this is basically it. This was the easy part, thanks to the fact that the GitHub repository is really well supported. It has all the instructions. It mainly uses the native PyTorch code, meaning that it will work on every device, on Macs, on GPUs, on CPUs. This is not the case for many other models where they would have some custom layer only implemented for CUDA, for example. So this is quite easy. So I'm going to interrupt it now, and let's talk about how to actually read the code. Right, so as promised, first I will talk about my debugging setup. So how do I set things up to make it easier? So first I'm going to Visual Studio Code. So this just opens the root of the repository, so you can sort of read the code, launch it, read the modules, and so on. So the first thing we need to do is to select Python interpreter. So if I just click here, you might notice that I have something like 8 different Pythons installed on my Mac. So I need to make sure that I use the same Python for PIP, for dependency installment, and in Visual Studio Code. So in my case, it's the one from Homebrew, the Python 3.9. So let's go with this one. So now I've selected it, and that will actually help you solve problems if it says something like Torch is not installed, for example. So that's one thing. Second thing, I want the debugger to work. So I've set a breakpoint here in the very beginning of the main function. And then I'm going here to the Run and Debug tab and press on Add Configuration. So it opens this launch.json file, which basically says what extra arguments you might want and what options. So most of this is just created by default, and then this line just was typed by me to provide proper arguments. So here I have to specify the Coco path and device, and that's it. So now it should work. So we can try to launch it again and just see if it works. So to do that, I go back to this Run and Debug tab, and I have to open the proper mode. So this launch.json was called Python current file, and this is the name of the configuration I have to choose here in Run and Debug. So I'm going back to main, I click on it and just push run, right? So here in the terminal, I can see that it runs, and it has stopped on this breakpoint. So I can see here the controls to step over, to continue execution until the next breakpoint, and so on. Oh, now it stopped. Yeah. I can go to debug console for some additional controls. So right now I want to print out the content of this args argument, for example, right? So here I only provided a couple of arguments with the dataset path and device. Most of them are default, but it still helps to just print out the exact content and just copy it and save it somewhere to be able to reproduce it later in Jupyter Notebook. So it is really useful. Another thing that I want to do is I want to create a Jupyter Notebook right in the root of the repository. So I'm doing that by just typing touch sandbox.ipython notebook, right? And this will create an empty file, but in my case, it already exists. And I will provide the link to the actual Jupyter Notebook that I use. So you can either just write it from scratch or just use mine. So this is it. So I placed it in the root of the repository, which means that I can now import the same stuff that is used in the main.py. So some of that is just third-party libraries, that's okay. And then some of these are actually referring to other files within the repo. So for them to be importable, I need the notebook itself to be in the root of the repository. So now I can just copy-paste that, paste it here, and it will work. Then I also have some helper functions. So I define the class names to be able to match the label to name of the class, like person, bicycle, and so on. And then the first one here is the extra class for no object. I also define the plotting function. So I need to be able to plot results to make it more obvious what is going on. So to do that, I have the unnormalized class, because actual tensors used in training are going to be normalized, which means they have 0 mean and 1 standard deviation. It's not really good for plotting, because plotting engine assumes that pixel value is always above 0. So if you just plot the normal tensor, you'd see a lot of just black spots. So all the colors will be off. You'd see like blackened image. So I do the reverse process of unnormalization to make it pretty. And here I just use the well-known mean and standard deviation values for different colors of the Coco dataset. You can see this stuff often in the code. Then just some helper converter functions. So Coco dataset provides bounding box coordinates in the form of coordinates of the center and then height and width. And I convert that to just coordinates of 2 points, and then the actual plotting function. So the plotting function will use the actual image tensor, then the actual labels, so the ones with the class for the object and the bounding box. So I convert everything needed and then just add a patch on top of that to draw the rectangle, and we'll see how that works later. Also, there is a thing for mask here, so I'll explain later why we need that. And finally, I define the args class and variable. So this allows me, the values I just copy pasted from here. So learning rate, backbone learning rate, and so on. I just copy pasted it from the debugger. And I define it in the special way as a class inheriting from namespace class. And I just instantiate it like this. And thanks to this, I can now call different function, just copy paste it from main.py like this. So now I can use this args variable the same way it's used here with the actual command line parsing. So I don't deal with command line and I'm not doing this. Instead, I just created this variable that contains all the same stuff. So now I can just copy paste everything from here and it will still work. Now let's talk about the first part in the training, that is the loading the data. What dataset is used, how do we load the data, how do we transform images, which augmentation techniques are used. So before reading the source code, I usually just imagine the main components that need to be there, because the source code of a real model might be quite complex. It is not that complex in this case, but sometimes it is. And it helps to have these reference points that help you structure the reading. And for a model, they are usually quite simple. So we load the data, and in PyTorch, that means that we have a data set that deals with the actual loading images from disk and so on. We have data loader, which deals with doing that process of loading data with some buffer to make sure that you don't wait for image processing during your training. It handles shuffling and stuff like that. Then we would have, so the data loader is something that you then iterate on. Then you have the model, which is something that you can call, feed in an image tensor and get the predictions out. Then you'd have optimizer. Sometimes you'd have learning rate scheduler attached to the optimizer, and sometimes you'd have parameter groups that allow you to control the optimizer behavior for different parameters. You'd have the main training loop, loss, and in the training loop, you'd probably iterate over epochs. Then every epoch, you'd iterate over training data set, then do some reporting for validation metrics, deal with checkpoints, and that's it. So if you compare this code to some of the other models like YOLO, for example, it is much simpler, partly because it was done by Facebook Research, the same company that created PyTorch. So a lot of stuff that is used here just refers to native PyTorch code. So for example, we don't have a custom logic for scheduler. We just call the torch function called step learning rate scheduler. We don't have a special data loader. We just call the native PyTorch data loader and so on. So the entire code is quite clean and simple. It's only about 100 lines if you don't count the argument parsing. And here you can just read it down and see all the main stuff we've talked about. So we define the model, and criterion is like a loss function. We sometimes deal with DDP, which stands for distributed data parallel. Not in our case, we just skip that. We have parameter groups. In here, we just differentiate between backbone and not backbone. We have optimizer, in this case, Adam, scheduler, dataset, data loader. Sometimes we load from checkpoints if we resume the training. And this is the main loop, right? So this is the overall code structure that we'll read in the next maybe 1 hour. So we start with the dataset. So let's just see where it is. So again, we have dataset train and dataset val. So you can just copy dataset train. We can see that it's only using the args variable, so we don't need anything else. And that's what I did here. So I build a dataset and it just works. And now I can get stuff from the dataset. So the dataset API is simple. It's like Python list. You can provide it with an index and it will return you something. In our case, that something is 2 variables. One will have an image, and the second will have a label. So here I'm printing the shapes of images, so the first one and the second one, and the example of a label. So you can see that images are different every time. So as any real world images tend to do. So they come from different sources, from cameras, from internet, and so on. So they all will have different sizes. And then for labels, we mainly are interested in just the boxes, which are bounding boxes, and the labels, which are numbers corresponding to objects. So every number corresponds to a specific class, like person, car, train, and so on. Everything else we're not that interested in, but Coco dataset actually has a lot of stuff going on. So apart from just object detection, it might be used for segmentation, which is when you have actual pixel values for every object. So which pixel belongs to this object, which is not. You would have the waypoints for pose estimation, for example, and so on. So sometimes you might see stuff like that in labels here. Again, right now we are not that interested in that. And then I plot the image and annotate it with the actual bounding boxes using the function that I've talked about before. So this is the first image in the dataset. As you can see, it's quite large image, high resolution, a lot of objects clamped together. So it's a challenging task. And then after that, I want to deal with the data loader. So if I go and just try to find the data loader in the code, I'll see that it uses batch sampler, this one. So random sampler. And that is needed because every time we iterate over the dataset in the next epoch, we want all the images to be in different order. We want different images to appear in the same batch at each epoch, which basically prevents us from maybe going in circles because we just randomly happen to get stuck there, or maybe from the model just remembering the batch setup and the actual images. So it's always better to just shuffle stuff. And also we have this collate function, which is also quite interesting. So we'll look at that in a minute. So first of all, yeah, I create the sampler, I create the data loader, and I can iterate over the data loader like this. So just type in like a for loop, just break after the first iteration, and then X is now available, and I can just print what it is. And this is quite interesting. So the type of X is now nested tensor, and the nested tensor, let's find it here. So it's not a PyTorch object. It's defined right here somewhere in the utilities file. So it basically allows us to load images of different sizes in a batch. So tensors have a tough time working with objects of different size because we like tensors to just have like look like a cube or a hypercube where every dimension will have equal length of elements for like every index. And because of that, because the actual images that we get are all of different sizes, we deal with that with nested tensors and masks. So nested tensor is basically like a wrapper around tensor that takes in various images of different sizes. Then it determines which size is the largest. And all of that, by the way, is happening in this collate function. So collate function in the data loader usually is responsible for the custom code that can be used to unite the different objects in a batch. So in our case, we have like the batch size is just 2. So we got 2 images with different sizes, and then we call the collate function to create a batch out of that. And here we call this nested tensor from tensor list function. So what it does is it looks at the input images, determines the maximum along every dimension. So what is the max height, max width? then it pads all the images to this max height and width, but it also saves the mask so that we know which of the image content is padding and which is the real image. So this is how it looks like in reality. So this is, I guess, the first image. So let's plot the second and see how it looks like. Right. So this is the second image. So the first one was probably bigger. That's why I didn't have this gray area. But now the first one is slightly smaller. So we padded that with zeros. After unnormalization, the zero, which usually corresponds to black color, changed to gray. So now we have this image padded with gray zones on each side. But we also have the mask. So if I print the content of X mask at 0, it will say false for those parts of image that were not padded. And then it will say true for those that are padded, so not real content. So you can see here that the upper left corner is all false, so it's real image, and then all the right side and all the bottom side is just padding. So this will be important once we start to deal with transformer and masks for that. What else can we see here? So we can see the actual image sizes. It's 608 by 834. We can, for example, compare that to what we had in ImageNet. So in ImageNet, I think we just resized all the images to something like 240 by 240 or something like that. So now the actual images are like 3 times smaller along every dimension, which is good. It allows the model to see more, to react better to smaller objects. It's also curious that the backbone of our model is just the ResNet. So the ResNet was trained on the actual ImageNet, so it only saw these 240 by 240 images. However, the actual ResNet model, which we call backbone here, it took the input image, then it applied a series of convolutions to basically scale down the size of the image and increase the number of channels. And then at the very last step, it had a fully connected layer. So as long as you have a fully connected layer in your network, you make it work only on fixed size images. So the actual ResNet would not be possible to apply it to an image that is not 240 by 240. However, for the backbone here, we just throw away the final part, the fully connected layer and the actual output, and we just care about this intermediate representation right after convolutions. And convolutions can be applied to anything. So every pixel in this intermediate representation can be seen as just sort of receptive area that is a function of input image somehow. And the actual process of applying convolution looks like sliding this filter along every possible position. And so you can enlarge your image infinitely, in theory, and it will still work. So you will enlarge your image. Your representation, the downscaled version of the image will also enlarge, and you are not confined by any specific size. So after you throw away all the fully connected layers from the backbone, you now can apply it to input of any size. But still, different networks deal with different sizes differently. So YOLO just resizes and sort of pads everything together to have images of the same size during training. That's not what we do here. In here, we actually train on images of different sizes without resizing and stuff like that. But we have padding to make sure that we train correctly. Also, let's look at image transforms that we had. So transforms are part of the dataset. So let's go to the code here. So this is build dataset code. It says build Coco, and it instantiates this Coco detection dataset. So again, there's only a bunch of lines here. We can see that mainly just inherits from torchvision.coco detection dataset. So it's really cool. It this class can be used to just load this image folder format that we had for Coco. So they have just a giant folder with a lot of images for train, a giant folder with a lot of images for validation, and then a separate folder with annotations for all the images. So this is the format, and the Coco detection PyTorch Torch Vision class already handles all of that really well. So it deals with loading the images, caching, validating, and so on. In here, so to define our own custom dataset class, we can inherit from this PyTorch class. We also re-implement two methods, so for init and for getItem. So init is the one called during construction, and then getItem is called every time we actually request an image specifying an index. And here we just do it to apply our custom transforms. And we also have this convert Coco poly to mask. So this one mainly is used just for segmentation task. So it's not really doing anything for object detection. And you can see here that this convert class also has some stuff regarding the key points, which might be used for like pose estimation and so on. But for actual object detection, it's not doing much. So we basically get the labels and we just return them. And the class itself is rather simple. So we just use the actual image loading from disk functionality from the native PyTorch dataset class. And then we have transforms. And let's see the transforms. They are built here. Again, quite simple. So they mostly rely on PyTorch native stuff. Again, unlike YOLO that had some stuff from augmentations libraries, some stuff just defined as tensor transforms writing code. In here, it's all clean and easy, just the Torch Vision transformations. And you can see basically resizes and horizontal flip. So this is how resize works. So the main method is usually random resize crop, but there are other alternatives that do just resize or just crop. So the idea is we have an input picture, we select pretty much random area of it, we crop it out, thus leaving some of the stuff out, and we also then rescale it a little bit. So we change the aspect ratio slightly. And we do that to make sure that the task is more challenging for the model, so it doesn't remember the exact images. It is ready for real world where you might be looking at objects from different position and so on. And then random horizontal flip is basically just flipping the image, like getting the mirrored version of it. So you can notice that the hand used to be on the left, and now it's on the right. And these are all the transforms that are used in DETR. So again, this is much simpler than YOLO that also had different color augmentations, mosaic, and so on. Now, as we've talked about the data, we have loaded it, we have the actual tensor that we can inspect and call the model on. Let's discuss model architecture. So this is the picture from the article with like the overview of the architecture. So we start with the backbone. So we feed in the image here. The output of the backbone is the condensed representation of the image. Depending on the initial image size, it can be something like 20 by 20 in height and width, and then something like 248 channel dimensions. We then project that down to 256 because 2000 is too much for a transformer. It's really expensive. Then we deal with positional encoding. So because the first step in here is basically to flatten out the image, we lose the positional information. And because of that, we explicitly encode that into the embedding itself. So the encoder is just the self-attention. So we have this flattened image representation of like 20 by 20, which got flattened to 400 sequence elements. So output of the encoder is the same 400 by 256 elements, basically creating the more refined image representation. Then we have these queries coming from the bottom that corresponds to basically our experts who are supposed to judge which objects are where. So we have this cross attention that we'll look at. The output again is 100 by 256. So now we went from the image dimensions to the number of experts dimension, which is always 100 in this case, which also means that DETR will not be able to detect more than 100 objects. And then we add a couple of independent heads, which are just dense layers, to project that to class probabilities and to bounding box predictions. So this is the code I've copied from main.py. So again, to build the model and the criterion and so on, I just need the args. So I execute it. It will load the backbone part of the ResNet from the Torch hub using pre-trained weights. The rest will be just initialized randomly. So here is just the overview of the model. Let's take a quick look of that. So it will have a transformer, encoder, decoder, then embeddings for query, for position, and then the backbone. The backbone, once again, I have a detailed video about ResNet, about how to train it. It has a bunch of convolutions, the so-called bottleneck blocks that use convolutions with the kernel size 1, which are just basically not propagating any information between pixels, but they still apply some transformation between channels. Then we have the bottleneck, which is the union of a bunch of convolutions with residual connection between them, and that's it. And so we are only interested in the final layer. So we're cutting off the fully connected layer, and we get this sort of condensed image representation out of it. And now we have our X. I place it to the same device, MPS, Metal Performance Shaders, Apple's analog to CUDA and GPUs, and I can just call it. It will work for some time, which is weird, and then I get the output. So the output is a dictionary. It will have logits, just class probabilities. The size of that is 2 for 2 images in the patch by 100. So I have 100 of experts. Each of them tries to detect something. And 92. So 91 for 91 classes in the Coco, and then an extra class for no object. And then bounding box detection is just the 4 numbers for 4 coordinates of the bounding box rectangle. Now, thanks to the fact that I sort of launch it from the same folder, from the same everything, I can now go to the model. So let me find the code for that. Go to definition, build. The model is defined here. So the model is a DETR. So it will be like multi-layered. So the outer layer is called DETR, which handles everything. And then it has big components like the backbone and the transformer. And then transformer itself has components like encoder, decoder, and encoder has components like self-attention, some fully connected layers, and so on. So let's just start with the very top, with the most generic piece, and then sort of dive deeper and deeper. So I can just put a breakpoint here, then return here and just say debug cell. No, not this one. I need the one where I call the model. So I have a breakpoint on the model call, so it should stop if I am calling the model, and it should stop at that forward method, and it did. So let's just print out intermediate shapes now and see how it looks like. So the call to the backbone returns features and position. So positional encodings are considered part of the backbone in this code, so we'll take a closer look at that a bit later. And we can see that features also contains the mask. So features is a nested tensor. Let's just print out what it has. So the type of it is actually a list. So the API is a bit weird. This function call receives a list of nested tensors. So we might have many of them, even though one nested tensor usually represents a batch. But then the length of features is just 1. So we can have features, the first element of that's going to be nested tensor. So I'm typing tensors to get the access to the actual image, and then .masks will give access to the mask. And I just print out the shape. So it's 2 by 248 by 32 by 26. So 2 stands for batch dimension, just 2 images. 248 is the channel dimension of this intermediate representation in the ResNet. And then the compressed picture is 34 by 26. So you can actually print the initial size as well. So we had a batch that got resized to 1063 by 813. So it's like the dimensions of the biggest picture. And then after passing through the backbone, we have 34 by 26. So we'll see a lot of these numbers later, 34 by 26, because we sort of keep passing that forward. Right, now we have this features passed through the backbone, and then the next call is just the transformer call. So that's it. So transformer represents the encoder and decoder at the same time here. The output of that should be the actual queries. So let's print it. So now this is an actual tensor, not a nested tensor. You can just print its shape, right? And now it's 6 by 2 by 100 by 256. So we know what 2 is. 2 stands for just batch dimension, 2 images. Then we have 100 queries, like 100 experts trying to detect some objects in the picture. And this again means that the DETR might only predict up to 100 objects. Then 256 is the dimension of the transformer. So we had to downsample our initial ResNet output a little bit to pass into that. But I also have 6 here. So 6 here stands for basically output of all the intermediate layers. So this is the scheme of it. So encoder also has several layers, but I'm not drawing it here. But this is the decoder. So we get queries passed from the bottom, and then the output of the encoder passed from the side to do the cross attention. And then the queries represent a sequence of length 100. And then I do a series of cross attention, self attention steps with some fully connected layers and residuals. And I do it several times. And I have 6 layers in total. But another interesting thing is that all the intermediate outputs are used in the loss as well. So you can think of these queries as having basically being experts, and after every step of cross attention and self attention, you expose experts to the image. So you let them sort of see the image and decide what they're seeing. You do self attention, so you let them discuss and refine their own representations. But you should expect that every intermediate layer already has some understanding of what is going on in the picture and what the objects are. So when we connect that to the loss, we are basically asking intermediate layers to do some good predictions as well. And it turns out it helps with the model. I'm not sure if the initial queries also do that. Maybe they do. We might be able to see it in code later. So we are back with our output. So right now, the embedding dimension of that is 256. And then we just do a couple of fully connected layers on top of that. So the class embed is, let's see what its type is. So it is just a linear layer, so fully connected layer or dense layer. And then this one is the same. Oh, it's actually an MLP. So it stands for multi-layer perceptron, which basically means a bunch of dense layers stacked together. So let's step through that. Right. An output class shape. The outer shapes are the same. So 6 layers times 2 images per batch times 100 experts times 92. So we had 256 dimension embedding, and then we want class probabilities out of that. So 92, that's one for an object class, and 91 for other classes in the COCO dataset. And then the coordinate outputs, bounding box outputs, only have 4 predictions per expert. And that's it. So this one returns. So this is the auxiliary loss I was talking about. So to actually save that, so the out here contains just the final outputs. But to get the intermediate outputs, I also call this set aux loss as well. So it basically what it is going to do is it will apply the same fully connected layers to intermediate layer outputs as well to get the predictions for the for the objects from the intermediate layers. So if we come back here, like embedding dimension of all of these is 256, right? So to get the class predictions, we apply fully connected layer here, and we also need to apply to intermediate layers as well, here as well. And that outputs the 92 numbers for class probabilities and then 4 numbers for bounding box coordinates. That's it. I can keep stepping through, and yeah, I'm in some weird place in Python right now, so I just press continue, and that's it. So I have returned to my Jupyter notebook cell. So basically what I did here is I have my model in the Jupyter notebook, I have my image, I applied model to the image, I was able to step through that in the debugger, and I got the predictions out. So this way we can debug Jupyter cells basically. But we only went through the top level, so let's go through the same a bit deeper. I'm going to press debug cell again. So the first thing that might be interested in is the positional embedding. So it happens inside the backbone, right? The backbone, let's see where it is constructed. It should be constructed somewhere here, right? When we are building the model. So when we are building the model, we construct positional embeddings, we construct the actual backbone, and then the joiner. So the joiner, as we can see here, it applies the backbone and then just looks up the required positional embedding and appends it to the output. So basically, the output of the backbone is this image, like 32 by 26 or whatever. And then positional embedding is basically a mapping from every possible position to a tensor, to an embedding with 156 dimensions. So we'll see how it looks like right now. And we need to look up, because the actual image is smaller, so we look up corresponding parts, like which parts of the image actually made it, are actually real. And we look those parts up in the overall positional matrix, and then just sort of append both of them. So both of them are returned, and we'll see how they add it together later. So let's go to this build positional encoding function. So this one is going to use positional embedding sign. Let's see the forward pass here. So this is the image from my previous video about positional encoding, sine, cosine positional encodings. So we have this input sequence here, which basically corresponds to small pieces of the original image for every pixel. Sorry, not original, but condensed representation with. And then, so for one-dimensional case, this axis will stand for, say, x, and then this axis will stand for embedding dimension. And so you can think of this as every element in the sequence will get its own 256 long vector. And so first element in that vector will depend on the position as a sine function with quite high frequency, right? And then, I don't know, 100th element within that will correspond to sine as well, but with much longer frequency. And then the last element is also just the sine, but the frequency is so high, is so low that you can barely notice that it's a sine. It just sort of grows slightly. So this is for one-dimensional case. And these sine, cosine, these coordinates within the embedding vector can be thought of as just basically knobs of different sensitivity. So think of, I don't know, a machine that turns the volume, but it has a lot of knobs. So the first knob, you slide it just a little bit, and the volume goes up by a lot. So it's really insensitive. You can get a lot of range from that, from really low volume to really high volume, but it's hard to set the precise number. And then you have the second knob that says that is less, that is more sensitive. So you have to adjust it to rotate it much more to get the same range. But now it's really sensitive, so you can really sort of control precise level of volume that you need in a really narrow interval. And then another knob is even more sensitive, and so on. So this combination of knobs basically allows you to achieve great range of possible values you can represent, as well as the sensitivity and like exact representation. So this is a bit excessive for the actual position because we just have like 100 elements within the sequence or less, but it still works. So and the reason we want sine and cosine, so this is the graph for sine, and it will have 128 coordinates actually. And we have the same 128-dimensional cosine encoding, and we just concatenate them. And the reason we want sine and cosine is that it's easy for the network to manipulate them. So if you think about how the network might represent relative position, for example, the formula becomes really easy when you have sine and cosine, something like you just square both of them and just take the sum. So it makes it easy for the network to use this encoding. And then if you have two-dimensional case, then you'd have x-axis, you'll have y-axis, and both of them will have their own sort of 1D positional encoding. So y encoding will have 64 coordinates for sine, 64 for cosine, and the same for x. And then every pixel in the image will get its own x-axis encoding and y-axis encoding, and sort of concatenate all of them together to get the 256 out. So let's try and see that in the code. So I'm going to break here, just press continue, and see what I have. So let's take a quick look of that. So we have our positional embedding object. It has some temperature, 10,000, and then this is the forward path. So let's iterate a little bit forward. So first we initialize the embedding. So the not mask is inverse from the mask. So the mask was an object of false and true objects, where false stands for real part of the image and true stands for the gray area that we added. So let's scroll down here, right? So we have an image. Down below, it is basically padded with zeros, and we are not really interested in positional encodings for this part. And this is the real image. So for the not mask, it's in reverse. So it now stands true for real image and false for padding. When I take CumSum, cumulative sum, I basically convert this Boolean tensor to numbers. So true will stand for 1, and then false will stand for 0. And take the cumulative sum. So after this, the y-embed, let's bring the shape. It's 2 by 34 by 26. So we have some coordinate stuff happening as well. So I basically have this 1D sequence of cumulative sum that should look like 0, 1, 2, 3, 4, and etc. And I would have that repeated over columns. And then the X embed will be also this 1D sequence, but now along different axes. Again, repeated, but now over rows. So let me just print the content of that for the first image. And here we can see that the first row is 1, 1, 1, 1, 1, 1, 1, and then 0, back where the mask was supposed to be. Then 2, 2, 2, 2, 2, 2, 2, and then again 0, where the mask is supposed to be. And then the final one, 34, 34, 34, and then again a couple of zeros. And that's for Y embed. The X embed would be the same, but transposed. Right. And we sometimes normalize it. Let's see what happens afterwards. So print out the same embedding. And now instead of 1s, 2s, and 34s, I normalized it in such a way that this last number is 6.28, and that stands for exactly 2 pi. So that's 2 pi, and that corresponds to basically 1 period of the sine function. So we start, we go up, we go down, we go up again, and then down, and then we stop. So this is going to be the highest frequency of sine that we use. So when I show this picture, I basically lied to you, and this picture keeps being copied from website to website, so sorry about that. But basically here it shows that the highest frequency is really high, so you get like 10 periods of the sine within the image, but actually it is just 2 pi. So the highest frequency you'd see here is just going to have 1 period. So it's probably pictured correctly on this layer or something like that. Right, so back to our code, I stepped through. So now DETR is now in the embedding space. So DETR.shape is just 128. Let's just print out the entire tensor. So it's 0, 1, 2, 2, 2, 2, 0, 1, 2, 3, 4, etc. up to 128. And then I use my temperature. So now it used to be from 1 to 128, and now it is duplicated. So you can see 1, 1, 1.15, 1.15, 1.33, 1.33, and we will use that later to get sine and cosine. So the first number, the even number, will be used in sine, and the odd number will be used in cosine, or vice versa. I'm not sure. And then now it is from 1 to 10,000, roughly. So the temperature used to be about 10,000. And now we divide by that. So now we get our pos x. The dimension t is in the denominator, which basically means that the temperature controls how the frequency falls. So in here it will fall by 10,000 roughly. So we started with a period of exactly 2 pi, and then it fell down by so much that it's really long, right? So you can imagine if you had smaller temperature, like exactly 2, for example, then the period will not fall that much. It will fall to something like pi, which corresponds to half of the sine wave. So let me step through that. And let's try to view this pos y tensor. So it's basically now the final one before applying the sine. So it will have basically the angle that we pass into the sine function in radians. So let's first try the shape of that. Shape. That's 2 by 34 by 26 by 128. So I'm going to try to print out some rows from that, right? So first I'm interested in the first image only. And then I want to say, let's print out the first row, the entire first row, and just the first coordinate. Okay, so it's all equal. So I messed up. I need the first column, not the first row. So let's try it like this. Right, and now I see it. So this is like the 0th element within the positional embedding is going to correspond to this lowest positional embedding with the highest frequency, which we determined to be 2 pi. And here we can see that it starts with 0, and then it goes up, 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 and then ends at 2 pi. So it doesn't change that much. So again, just exactly 1 period of sine function. Then if I look at the second one, it's almost the same. Then it starts to go down a bit. So now it's from 0 to 3. So it's almost pi. So it's now like half of period. And then for 127. The last one, it's almost 0, so it's barely changing. Then we apply the sine and cosine to it. Let's print out the same tensor, the first coordinate. Sorry, once again. Yep. So now it used to be just denoting angle from 0, just rising up to 2 pi. And now it should be the actual sine function. So it goes up, up, up until about 1. Then it starts to go down. So we went up, and then it starts to go down. Then it went down, and then up again, and it stops at 0. So it's half a period, as promised. No, actually, 2 entire period, sorry, like this. And then again, if I look at the coordinate number 10, it's still the same pattern, but now the period is slightly lower. And then the final coordinate of that, so it's a cosine, and then for the sine, yeah, it's barely changing. And that's it. We return that. So we concatenated position y, position x. We got 256 tensor out of that. Let's just confirm that. Yep, so it's 256 by 34 by 26. And this is the positional encoding layer. So it does not use any trainable parameters. It just basically initializes all the numbers it needs to represent position, depending on the actual image that we've seen. Sorry, not the image, but positions within the image. So it's not actually using any pixel information. So that was the deep dive into the first thing we wanted, that the positional encoding. Now let's do the same for other parts of the model. So starting with this plus sign here, where we sum up the output of the backbone with the positional encoding, and then the actual transformer layers. So transformer encoder, transformer decoder, and the final output. So I had this breakpoint in the beginning of the DETR, so let me just remove that. Then I also want to go back to the build model code. It calls build. And here I can see that DETR is the model we just looked at, the outermost layer, and it just receives this transformer as an input. So let's dig into that. And this transformer returns the model called transformer. So this is the one that actually defines transformer encoder, decoder. So encoder consists of several encoder layers, and then decoder consists of several decoder layers, and so on. So again, let's just break on the forward pass here and see what we can see. Right. So I'm still at the call function for the model itself, and I am in the beginning of the forward method for transformer. So now we've received the source tensor. That should be the actual tensor. Let's confirm that. The mask, positional embedding, and then the query embedding. Let me come back to DETR. See, where was the query embedding? Right, so the query embedding comes from the DETR model, and it's called just embedding here. So it's pytorch.nn.embedding. So this is the docstring for PyTorch embedding, and it basically just defines a lookup table. So input to that is just a number from 0 to 100, and then you provide it with the number from 0 to 100, and it outputs unique set of weights. And these weights are trainable. Now we are back to transformer, and let me just print out the shape of the query embedding. So it's 100 by 256. So we have 100 queries, 256 embedding size. So then we step over and we do some data transformation to change the shape, not change the content. Then we do this repeat function because we might have several images in the batch. So we repeat the query embedding for every image. Then we initialize the target in the same shape. and then we call encoder. So this is still quite a high-level code. Now let's just look at what the output is. So the input to this is just src, which was the initial image. So we had something like 34 by 26, and I believe that yields the 884 size. Oh yeah, that's how we did it. So we had the source, and we flattened it. And then we pass in the mask and the positional embedding. And so the output of that should be of similar shape. This is just the refined representation of the image. So let's step through that and print out the shape for this. Right, so it's still the same shape, 884 by 2 by 256. And this is the quick reminder of what happens in the encoder. So as input, we have this sequence of flattened part of the image, each being represented by a certain embedding of size 256. Then we project each of them individually through the query layer and the key layer. Then we calculate a dot product between each possible pair, this one and this one, this one and this one, this one and itself, and so on. So every possible pair. We get this attention mask. Then we do this projection step again for every element in the sequence using the third dense layer called value. And then we multiply that with the attention mask, which basically means that for a certain row in the output, for the certain element of the sequence, so ith, we look up the corresponding row in the attention matrix. So it will have just a bunch of numbers with the same lengths at the sequence, so 884 in our case. And then we use those numbers for weighted sum. So we do a weighted sum of all the values we had to get this one output element. And then we repeat the same for all the output elements. So the result of that is just, and that's just one encoder layer. We repeat that several times. The result of that is the same shape, basically refined representation of the image. And then we apply the decoder. So decoder now will have a different shape, 6 by 100 by 2 by 256. So now this is how decoder looks. So encoder just outputted this memory, which is like the final sequence from the encoder. After this, the memory remains unchanged. It is passed as a side input, which means it's passed as key and value to every cross attention layer in the decoder. And the decoder itself starts with our randomly initialized vector of queries, 100 of them. And then they go through this series of cross attention, self attention, dense layers, residual connections, and so on. So the input to this one, the normal input, not the sign input, has the sequence length of 100, and the output is the same, also 100. But we also have this extra addition to the loss where we output every intermediate layer as auxiliary output to use that in the loss as well. And then we return all of that. Okay, I've returned to my cell with just calling the model again. So again, this was quite quick because we just had encoder layer, decoder layer, but we've seen the shapes of input and output. Now let's try to dig deeper into the actual layers as well. So let's take a quick look on how they are constructed. So we have this encoder here, which gets encoder layer as an argument. So let's remove this breakpoint and look at the encoder itself. So when it is built, it receives the encoder layer and number of layers, which is 6 in our case, and then just clones them, right? And then it does the forward step. So let's break at the transformer encoder forward step somewhere here and see what happens. Right. So now we have this. This is encoder. So input to that is the sequence with the length 884, corresponding to just flattened pieces of the image. So let's confirm that. 884 by 2 by 256. Then we initialize output as the current source, the image, and then we just call the layer. Right. So everything important happens in the layer, but we can see that we just rewrite the output variable. So output of the layer is the same shape of the input. So we just compute the output and save it to the same variable and repeat the process 6 times. So let's now break at the encoder layer forward path. So it has 2 forward methods, one where we normalize after the attention and one when we normalize before the attention. So let's just break at both of them and see which one actually happens. And this forward post is the one that happens, right? And so input to this is the source, so the tensor with the actual images, and the positional embedding. And then we call this with positional embedding function, right? And you can see here that all it does is just sum them up, which is curious. So we are not projecting the positional embedding with anything extra. We don't have any trainable layer on top of that. So we can print out the entire first column, for example, in the first coordinate of that. And this is exactly the sine function that we've seen before. Only now it's a bit flattened, I believe. Yeah, because the source is flattened as well. And we just sum that with the image representation, which is a bit weird, I guess. So if we come here, now we had our backbone that outputs some good representation of the image. We have a projector layer on top of that to project it down to 256. So we give our model the chance to decide how it is going to use this embedding space. So it might use the first 254 coordinates for just the image, all right, and then focus on the rest and just leave 2 for the positional encodings. But the positional encodings are not passed through any other layer. So basically you have this embedding for the image, and then every position here gets spoiled in some way with this positional encoding. So I guess it's good that the last coordinates don't have that high numbers. Maybe you wouldn't need that high temperature if you just allowed an extra trainable layer here, but I don't know. So now we added this positional encoding, and then we just call the self-attention block here. Self-attention is defined as PyTorch multi-head attention. So again, this is the native PyTorch function. So this is the definition for it. So it receives basically query, key, and value. So 3 vectors, 3 embedding sequences. And then we say which embedding dimension we need and how many heads during initialization. And in here, we call it with query, key, and value, right? And we can see that query and key are the same as source with positional embedding, but then value is just the source, which is interesting. So for calculating the attention matrix, we use this position information, but then to get the actual sequence of outputs, the actual value has no positional encoding, which is interesting. I didn't know that before reading the code. We could also try to look into the actual multi-head attention layer as well. It is going to be quite tough because this is not our scientific code. This is the actual PyTorch code. You can see here a lot of ugly implementation details. So this is the forward function, and it is going to be really, really long. So we can see that sometimes they have this fast path when some conditions are met, and you might just do that in native CUDA C++ code. Sometimes you would call, and like this one, the native multi-head attention, and there's just some C++ binding, I believe. And then sometimes you would have this non-native code that now calls the functional multi-head attention method, right? And again, it is really, really long, like 1,000 of lines. But the actual piece where the calculation happens is somewhere here, right? This BMM. BMM stands for batch matrix multiplication. So if I come back to my slide where the attention happens, what you basically do here when I'm saying that you need to do this dot product with for every possible pair, this operation is actually really well represented by just matrix multiplication. So you have this huge matrix of size batch times sequence length times number of heads times embedding per head, which is like 32, I believe. And you have another matrix like this again, batch times sequence length times head times embedding. Oops, it's getting deleted. But basically, when you do the matrix multiplication, the batch matrix multiplication is basically going to remove the last dimension. So it will calculate the dot product for every possible pair within these batches and within the heads. And the output is just what we need. So it's basically this dot product of query and key calculated over all possible pairs within the sequence, and then for every batch, for every head. Unfortunately, in my case, the actual execution goes only to the native code, so I'll not be able to just go there in the debugger. But at least the code is here, so you can actually look at what is happening here. So let's just see what happens. So again, this is the beginning of encoder layer. So we added the positional embedding to some sources. We computed this self-attention. Output of that is just the same as the output of as the input. Then we do dropout normalization. Then this SRC2, which basically is needed for residual connections. So now SRC2 was the output of self-attention. And then we compute the result of that as initial source plus dropout out of SRC2, which means that we had this output of attention. We now have this residual connection and dropout. So we apply dropout to the output of the self-attention layer, and then we also add residual connection. And then the same for linear. So we have an extra linear layer on top of that, just to be sure. And again, we do this residual connection trick. And we also have the norm. So two interesting things here for those that stayed in computer vision and object detection for quite a long time. So in other models that we've seen, like YOLO, like ResNet 50, and so on, we use batch norm, and we don't use dropout. And here we can see that it uses layer norm instead and dropout. So let's discuss that. So someone actually answered this question on Stack Overflow with a really cool image that helps you visualize that. So batch norm, let's say you have a layer with, let's say, 256 dimension of embedding. So you have 256 outputs of this layer, the coordinates. Then you'd have the batch dimension. So you'd have 256 outputs for every image in a batch. And then in our complex case of transformers, you also have this third sequence dimension. So what batch normalization does is it computes the standard deviation and the mean for the batch dimension. So you look only at one particular coordinate within the layer. but you look at all the images within the batch to compute this mean and standard deviation and to normalize the layer. So this is called the batch norm. And then the layer norm is when you only look at the current image. So you are not looking to add other images in the batch when computing the mean and standard deviation, but you look at all the coordinates within the layer. And there are some reasons actually explained here why that happened for language transformers, because you might do next token prediction where you're not supposed to look at what happens next in the sentence. And then if you also look at different examples in a batch, it becomes weird. They all might have different sequence length. They all might have information that you were not supposed to look at. So it was easier to just use layer norm. I'm not sure if that is actually the case for images. It looks pretty safe to use for images, but we just use the same because it's just the common transformer block. So we use layer norm. And another thing here is that when you use the batch dimension for normalization, you basically introduce some randomness into the process, because the batch will be different every time you do shuffling. And because of that, these norms, the mean and standard deviation, will have some noise in them. And because of that, you basically have the regularization happening here. So you add some noise to this layer, and that makes the job harder for the model. So it cannot just remember the picture. It's harder for the model to overfit. And that was the reason we didn't use dropout before in ResNet 50, for example, because batch norm in itself is a good regularizer. And now, when we don't use batch norm, when we use layer norm, we don't have that anymore. So we have to use something extra as a regularizer. So here we use dropout. Dropout basically zeroes out random coordinates in the output, something like 10% of them. And that, again, basically prevents the model from overfitting. And that's it. So we can see dropout, linear layer, and that is the output of this encoder layer. Another thing I wanted to mention here is just the number of trainable parameters in the multi-head attention. So as we discussed, this is like the juiciest part of the entire model, and unfortunately it's all implemented in the PyTorch code itself, so it's quite hard to read, but we can at least look at it from the outside and try to determine what is going on there. So this is saved as self.self-attention. Let's read the code one more time. So during initialization, our parameter weights are initialized here. So in case we have different query key in value, we'll have different tensors for that. In case of self-attention, we have one big tensor with 3 times the dimension. So let me print that out. So it is 768 by 256. So basically, it doesn't depend on the sequence length. It's basically this 256 by 256. So we project an element of length 256 to the same embedding size. And these query key and value weights are then reused for every element in the sequence. So what we were doing here when doing the projections, when I said that we're going to project some element to the value representation of it, and then add that with some attention weight to the output, and then another element will be projected to this value. All these projections to value from the initial element in the sequence, they all happen using the same set of weights, the same dense layer, basically. Right, now let's look at the decoder. So let me remove the breakpoints here. First, a quick look at the decoder itself. So now, again, decoder is like a wrapper around individual layers that are passed in from the outside. And here it is slightly different. So again, we iterate over all the layers in the decoder. There are going to be 6 of them. So we just initialize output as the target at first. And if we look at the code for transformer itself, the target basically starts with just zeros. So we have these zeros coming from the bottom as basically our query input. It is going to be added to the actual query embeddings at some point. And then we compute this output of the decoder layer 6 times. And then we also have this logic for intermediate results. So return intermediate is going to be true, which means that when we do the decoder layer forward pass, we save outputs from all the individual layers as well. But the most interesting part happens in the decoder layer. So let's make a breakpoint here. Again, it has just forward and forward pre. So let's break at both of them. Press continue. And we can see that the normal forward is the one that happens. This one. So I'm going to forward post. So this is the one that happens by default. Now this, instead of positional embedding, I have my query embeddings. So again, at the very beginning for the first layer, the target is initialized as 0. And then for every layer, I'm going to add the query encoding. Then I do self-attention, dropout normalization, then multi-head attention. Again, dropout normalization, and then return that. So a couple of interesting pieces here. So self-attention is basically the same, but now instead of operating over this image sequence with like 884 sequence length, I have my query input with just 100 elements. And I just do self-attention. So let's see where it is defined. Yep, this is just multi-head attention. And then we have a second attention, which will be used for cross-attention. Again, it is defined using the same PyTorch module called multi-head attention. But now when I apply that, I have my query, I have my key, and I have my value. And so memory is this fixed encoding output, so the final representation of the image itself. And it is passed into multi-head attention to cross-attention as a side input as key and as value. But then key is used with positional encoding, and value is just used as is. So let's print out the shape for positional encoding, for example. Yes, it's 884 by 2 by 256. So now this is my slide for cross-attention. So we use the actual image sequence, actual pieces of the image as query and, as key and value. So we first use it as a part of attention mask calculation, where the key comes from pieces of the image, and then a query comes from the input experts, let's call it that. And we also have seen in the code that when we do this key calculation, we also add the actual positional embedding from the image. And then when we do the query calculation, we use our query embeddings as this extra step. And then when we do the second step of cross-attention, we now computed the attention mask in the previous step. And then again, we take the value from the image, but now without positional embedding. And we use this attention mask to project that from whatever it was our image sequence length down to 100, which stands for sequence length for the query. So other than that, the code is pretty similar. So basically, again, the majority of the calculation happens in this self-attention block and multi-head attention block. All of them are actually the same function, but in case of self-attention, we basically pass the same tensors as input, almost the same, right? So here the key and query are equal, and then value is the same, but without this query embedding. And then during multi-head attention, query, key, and value will all be different. And that's it. So this is the majority of the encoder-decoder code. Let me just remove the breakpoint and return from here. And now let's also discuss loss. So here's a quick reminder of the problem we're trying to solve. So let's say we had two birds on the picture, and we have two ground truth objects, which with classes and bounding boxes, and then the model outputs something. So in the very beginning, it will be just random. Then at some point, it will be quite good, but still not entirely correct all the time. And we need to deal with this situation where the model has predicted more objects that there are, and we're not sure, like, should we match this bounding box that seems like a good match for this bird, but it says it's a cat, or maybe this bounding box instead that has the class correct, but then the bounding box prediction is worse, and so on. So how do you do that? We do that using the bipartite matching loss. So basically, we had our set of ground truth objects and the set of model predictions, and we need to find such connections such that every one of those nodes is used only once, and it optimizes some sort of loss. So the actual connection is done using the Hungarian matching algorithm, also called matcher in the code. And the actual loss consists of three terms. So we have classification, basically just cross entropy between predicted class and the actual class, where the class can be person, train, dog, etc., or no object. So no object is a special kind of class that is also taking part in cross entropy. And then the two terms for bounding boxes. So L1 loss, which basically just measures the distance between predicted 4 points for the bounding box and the ground truth 4 points. And then GIU, which stands for generalized intersectional union. This is just differentiable alternative for IUU, which is the measure of overlap between the boxes. So let's come back to our code, right? So we just were looking at the predictions. Now, we also constructed this criterion as part of our build model call over here. So now let's save the outputs of the model somewhere so we can use them. And this is again how they look like. So outputs is the dictionary with a lot of stuff inside. So it will have final outputs for class probabilities for bounding boxes. And it will also have the set of intermediate outputs of intermediate layers as well. And then we just pass that dictionary onto the loss, to the criterion, and that's it, right? So we can just run this cell. It will calculate all the losses. So here we have 25 of them. Some of those, like this cardinality error, is actually only used for debugging. It's not taking part in final loss calculation. Then loss CE is the cross entropy for the final layer. Same for GIU and bounding box. And then we have the same three alternatives for every intermediate layer again as well. So first layer, second layer, third layer, and so on. So now let's see where it is constructed. So here's our build model code. And so it has the set criterion, which is the actual loss, and then it receives a matcher from this build matcher code. So let's first look at the matcher. So the matcher is the Hungarian matcher. Let's just put one breakpoint here, and then one in the forward pass of the set criterion as well, right in the beginning. Right, so now I can just click debug cell and something will happen. Right, so the first thing we notice here So we start, we get this dictionary of outputs, we have our targets. Let's print what that is. So targets is just a list. The first element of that is just objects for the first image. And then the second element is object for the second image, and each object knows about bounding boxes, class labels, and so on. So first thing we do here is we actually construct a different output without AUX, so without intermediate layers, and we pass that one into matcher. So we've promised that Hungarian matcher will optimize the final loss. In the code, that's not entirely correct. So the final loss takes all the intermediate layer outputs as well. Then the Hungarian matcher only looks at the final output. So that's the first difference. Let's just step through that and see what happens inside the matcher. So let's just iterate a bit forward to understand what it is. Right. So first, another difference between the matcher and the final loss that will be used is this classification loss. So in the final loss, that is supposed to be cross entropy. In here, we just approximate it with 1 minus probability. So this 1 minus probability function should look similar to the negative log likelihood. So at least it sort of changes in the same direction, but the actual curve itself is different. So we don't really have the guarantee that the minimum of this criteria in the matcher will be the same as the minimum of the final loss, but we still sort of use that because it seems to work and it's easier to construct that way. Then we calculate these 3 cost terms and then add them all up with some weights into the final matrix. So let's print the shape of that. So it's 2 by 100 by 9. So we have a batch of 2 images. For every image, the model outputs 100 expert predictions. And then we have 9 objects in total for 2 images. So this matrix actually contains all the intermediate cross predictions. So it also knows the loss for predictions of the experts from the second image with respect to ground truth objects in the first image, which is a bit weird. But then it is fixed in this line where we do this split here. So during split, we actually split those batches so that only the experts from the same image are calculated in the loss. And then the main part of that is this linear sum assignment, which is imported from SciPy. So here's the doc for it. This is basically the SciPy function that receives a matrix as an input, matrix corresponding to these graph connections in the bipartite graph with the cost function associated with every edge. And then it does this Hungarian matching algorithm that finds the optimal match. So all of that stuff is happening inside this function. We will not read the actual implementation. And then after that, we just have the indices. So let's print it out. This is just a small array that actually shows which ground truth objects match to which expert predictions. And we return that. Then we come back to the actual loss function. And here we can see that we basically iterate over all our losses defined here. They basically calculate the loss that I've talked about before. So the classification loss, bounding box loss L1, bounding box G IOU loss. And then we do the same for all auxiliary outputs. So not much interesting going on here. And then we return that. Now, I also want to talk a little bit about how training is done. So if I come back to main.py, again, this is quite clean code. It's more or less easy to read. So we have our model, we have our data loader, then we have our optimizer. Someone who had studied object detection models, this might become interesting. So other object detection models like YOLO, like ResNet, they usually use stochastic gradient descent, so SGD optimizer. In here we use Atom. It works slightly differently, but the overall concept is still the same. It basically calculates these running momentums for the gradients and uses them to dynamically adjust the learning rate as well as to capture the overall direction of the gradient descent. And that seems to work well in some cases, better than just SGD with momentum, and then not so good in other cases. So we tend to use SGD with convolutional based models. But then as soon as you have a transformer, you'll see that most of the actual models start to use Atom instead. Then we have this step LR scheduler that basically decreases learning rate by something like 10x every few dozen steps. So the actual learning rate looks like this ladder that just goes down little by little. And then if you look at the actual metrics like average precision, it will go up in these steps as well. So it will saturate for a given learning rate, and then after adjustment, it will go up a little bit further, and so on. Then we also have the sampler. We construct our data loader. The actual training happens here. So we iterate over epochs. For every epoch, we call this train one epoch function. The function itself iterates over the entire data loader. It gets the images, puts them to device. Then we call the model to get model predictions for the given images. Then we calculate the loss using our loss function or criterion, as we call it here. So the loss is a dictionary. Then we just sum them up to get one final scalar number. Sometimes we do this scaling. Then we do zero grad to zero out previous duration, do the backward pass, and optimize a step to update model parameters. So all of that, I think by now everyone is pretty much used to that. So this is all I wanted to talk about today. I hope it was useful. Again, today we had an introduction to the code. So I have my previous video with a more straightforward explanation of the actual model algorithm. So if you don't understand some stuff that's happening right now, you better return to that video. But I hope that it's useful because you might want to implement a model like that yourself. You might want to just make sure that the benchmark reported is correct. You might want to consult the ground truth. And again, source code is the ground truth. So it is better than the paper. It is better than different YouTube bloggers. So it's good if you can just go ahead and read it on your own. And I'm hoping I can help with that. Next up, I'm going to talk about more stuff for object detection. So one of the things I want in my channel, apart from just explaining some algorithms and helping to read code, is to set out the learning path. So you can start from somewhere and you're not sure how the overall field looks like. And then I will guide you through different aspects of that and help you get somewhere. So for now, I've made a bunch of videos about image classification and object detection. So we started with just simple introduction to PyTorch with digit classifications that you can just sit down and train and code down yourself in half an hour. Then we threw in a lot of deep learning concepts like optimizers, loss functions, activation functions, all that stuff that was actually needed to be able to train proper models. Then we had our first big project for training the actual ResNet 152 on the ImageNet dataset, the big 150 gigabytes dataset, and I have a video about that, about reading the code for that as well. Then we moved on to object detection, that is detecting bounding boxes for multiple objects in the picture. I have videos about YOLO, I have videos about DETR. And then I wanted to sort of split out future videos into two directions. So the first one will continue exploring various models in object detection. So the very next one is going to be called Deformable DETR. So this is the Papers with Code website that basically reports the current leaderboard for Coco dataset. So the actual DETR is somewhere here at 40. So it's not the best one at the moment. YOLO that we've seen before is somewhere here. And then state of the art is this one, the CoDETR. And this model actually has a bunch of new concepts in that were introduced over the past 3 years, maybe. So deformable attention, dynamic anchor boxes, denoising, all that interesting stuff. So I will make a bunch of videos about those to sort of set up the foundation for everything we need to know in order to discuss the actual current state-of-the-art model. And the very next one will be about deformable DETR. At the same time, I wanted to start the branch about generative AI. So the very first video in that branch will be about neural style transfer. This is quite an old technology. I think it originates back in 2015. And it sort of branches out directly from ResNet, so we will not need advanced concepts like transformers and so on that we've talked about in recent videos. But it's still really interesting, and it sets some foundations for future generative AI videos I'll have. And then we'll move on to more interesting stuff like unconditional image generation, where you just generate an image similar to what you've seen before in the dataset, and that can be done using variational autoencoders, diffusion, GANs. And then there's a long road towards image generation with text prompt, for example, and stuff like that. So I hope that sounds interesting to you. Hope to see you soon.